Okay, hello everyone. Thank you very much for the opportunity of giving a series of talks here. I was very pleased with the program and what we could do. So yes, myself, I'll be talking about Chabauty method. So the first original one, classical, and quadratic, which is a much more recent. And today it will be mostly introduction and setup. So before I start diving in notation, I guess, as well as some of my colleagues, I'll say a lot of things, some of which I don't have time to enter into too much detail, but I've written some lecture notes, short ones, which I will make available after each talk online. Okay, so for some details, not all of them, but more details, you can read a bit after each talk. Okay. So the notation here will be the ones I will use for the 4 talks to get the same context every time. So I'll start with a curve, C, smooth projective. With a genus that's at least 2, so it's not an elliptic curve because elliptic curve we do other things. I also start with a curve of a Q, even though we could do everything over a number field. It's for simplicity. Methods can be stated and at least tried over number fields. Okay, what we know about such a curve is that the set of rational points is finite. This is due to Chabauty's theorem in the 80s, but as you might know, this theorem is not at all effective. It can, when adapted, give a bound on the number of solutions, but the bound is huge. I don't think there is any example where it's reached. And it doesn't help you to find the rational solutions at all. So the question is, the goal of what I'll present is to determine C of Q effectively. Effectively, I mean, find the solutions and know there are no other ones. So to do this, I'll take all the time as well a prime number P as a good reduction of the curve. In some sense, if you have equations defining C, it means you can find integral coefficients for them and find a good way of reducing modulo P, that the reduction as a curve over Fp is also smooth, projective of genus G. Okay, I'll not say much more about this, but it's a good prime. Almost every prime is a good prime here. So now I can state the very general principle of Chabauty methods of how to do this. Well, the idea is basically to find, I'll leave a blank space here for now, p-adic power series isolating the rational points inside the p-adic points. And of course, I don't hope to have one power series for the whole curve. So I should say they are local. So the goal is to split this set, which is a curve over QP, so one-dimensional object, split into finitely many parts. And on each part, I want to have a power series whose zeros will contain the rational points in there. Okay, if we can do that explicitly, we'll know, I'll explain a bit later, that's a non-zero power series, in this case, has only finitely many zeros in this kind of sets. So I have finitely many zeros per small set I've chosen, and I gather them, and I'll get finitely many elements containing C of Q. So that is the goal. I want to start with a very general object and find explicit power series to help me figure out rational points. Okay, so that is the goal, but not very easy to do in general. I'll start with some more notation before I really write at least classical Chabauty. So first, I'll use a bit of vocabulary of schemes. For a scheme over spec A with A ring and B in A algebra, chi B is the base change of chi to B. If you don't really know what it means I will allow myself to change coefficients between fields, for example, for Q to C, or reduce coefficients mod P from Z to Z over PZ, etc. I'll do that with the objects here. All right, given I have good reduction, by the theory, there exists a smooth projective model of the curve C, which is defined over Z P. So here, which means I have coefficients in this, this ring, and I can reduce them mod P and obtain something that is smooth. And if I just look at it inside Q, I get back C here. And why do I do that? Is because I can now properly talk about the reduction of the curve mod P. By abuse of notation, it will be this, okay? And the points over FP, so the solution mod P will be, again, by abuse of notation, this. Okay, something else I can do when I have this kind of objects is if I have P points in C of Q, or actually QP works as well, I can reduce mod P which is denoted by P bar here. Okay, this is the kind of thing I'm allowed to do, reduce mod P points. And I'll start by figuring out what kind of points land inside the same point here. So for X inside C of P, F of P, I call dx the set of points in QP such that P bar is equal to X here. And this I will call, it's a quite important object of study, the residue disk of X. I'll explain today why we can call it a disk, why it's not too weird to call it this way. All right. And now one of the main objects I will use is the Jacobian. So Jacobian of C. So we've talked about elliptic curves before. Professor Gatte mentioned. A Jacobian is something that behaves like an elliptic curve, but with a higher dimension. It's called an abelian variety. Okay, a first way to think about it is that, in some sense, it is the set of divisors of degree 0 on the curve. Okay, so this set can be endowed with the structure of a group, actually an abelian variety. It has a lot of properties. For now, I'll just say that dimension, the Jacobian, is equal to G. All right, and because I need it for simplicity, I also fix B, a rational point of C, which I call the base point. And this allows me to send the curve inside the Jacobian in the following way. To every point P, I associate the class of the divisor P minus B. So this is a degree 0 divisor in the curve, so it makes sense to talk about it in J, which parameterizes those two equivalents. So this is an embedding. All right, now I can explain what is the main idea behind classical Chabauty. actually, many things can be summed up in the following drawing. So I want to understand this. Okay, first thing I can think of is embedded inside the rational points of this. Why is it interesting? Well, because this has a group structure. So this is a group, and it's actually even a finitely generated Z module. Okay, so you can find finitely many generators. This can be studied pretty well. Okay. Another idea fitting with this is well, we want to look at it inside C of QP. This is sort of better because it really is a curve over a QP, so it has a more analytic structure. All right, well, why not do both? Why not see it both in the same time? How can I do that? Well, I need to find a space containing both here, and the natural candidate is this. Not the rational points, but the QP points of the Jacobian. This. So these are inclusions. This is the embedding I defined before. So you get a vision of C of Q sent in both ways inside G of QP. And to be more precise, iota of C of Q is included in J of Q intersected with iota of C of QP. So I intersect a group with something that has a one-dimensional analytic structure, and I hope it's enough to say it's finite. Well, in general, it's not, but the good thing with Chabauty is that you can exploit it. So I write some few facts here. First, G of QP. It behaves, if you know about Lie theory or Lie groups, well, this is a p-adic Lie group, and it's compact. So by p-adic Lie theory, it looks like this. It's ZP power G plus a finite group torsion. Now, J of Q inside this, by Mordell-Weil theorem, it's something with a Z power R with R finites. So R is called the rank of G of Q. Okay. And you hope that this is small enough in this. A good way to state it is that R should be less than G. And what can we say when R is less than G? Well, that's the idea behind Chabauty, is that if R is less than G, there should be, and bear with me for now because for now it doesn't really make sense, but if R is less than G, we want to say there is a linear equation of G of Q in G of QP. Okay, if you just think about this and this, you have ZR inside ZP power G. If this is smaller than this, you can find coefficients in ZP vanishing, making a linear form vanishing on this, but not zero here. All right, so let's call it L here. First, maybe I should mention, why do we do all this over p-adic numbers? Well, we can try the idea over real numbers, but at this stage it fails. At this stage it fails. It's a good exercise maybe to understand why it fails. Even if the rank is small, if it's 0, you can do things. Even if it's 1, you should not be able to find something like this. When you think about it, it's a good exercise. So, but over p-adic numbers, it works. And that's what Chabauty obtained in 1941. So in this case, it's of course much earlier than Faltings, but under this condition, that if the rank is less than G, so the dimension or the genus of C, the set of rational points is finite. All right, so maybe opinions differ regarding this, but I'm not sure that as written, it's really effective, even in terms of counting the number of points. Chabauty's paper, it's not clear, but it has been revisited by Coleman in the 80s. And now it's much clearer and we can get it effectively. So I give the principle of the proof and I'll get back to it tomorrow actually. So take such a linear equation. So what I've said is that C of Q is inside L composed with iota minus 1 of 0 inside C of QP. Well, again, some more facts. For every x FP point of the curve, dx, what I call the residue disk, can be made isomorphic, so by bifurcation, sorry, with PZP. And this is actually a disk, if you think about it. It's the disk in QP, closed disk around 0 with radius 1 over p. So that's why we talk about the residue disk here. And now we can think about this. And now, why it's interesting to think about this? And this function restricted to dx can be written as a p-adic power series. Okay, so on each residue disk, I can write a p-adic power series for this. All right, it's not enough yet. Now I use a second very important object, is that there is, as for the usual situation over R, but even better, there is a logarithm map which goes from J of QP to the tangent space of JQP, right, which is isomorphic to QP power G. So log, which is an analytic map and a group morphism with the obvious addition here. Okay. And now I can write properly what this means here. Actually, I can write L is equal to L prime composed with the log with iota with L prime, an actual linear form here. So the dual of the tangent space, non-zero. Okay. So I could not really talk about linear form here, but this makes sense. Okay. And now what's more is that on each dx, if I look at this, so yeah, so yes, L is L prime composed with log, yes. Each dx, L composed with iota, here is transcendental log iota. It's transcendental, which means the image can never be contained in the zeros of a polynomial here. Okay, which will mean that you're not allowed, if you take just a linear form afterwards, which is what you do, you should not get 0 on a full dx. Okay, so in particular, not the fact. So L quad iota restricted to dx is non-zero as a power series. Okay, now we have a non-zero power series, a p-adic power series on each dx that vanishes on rational points because of this. Well, we know how to bound number of solutions of power series on each residue disk. We have a bound, and we gather the bounds because, of course, this set is finite over FP. So we get first dx, so Q is finite here, and then Q is finite. Here we go. So to be more precise, maybe, if we want to use everything we can have, we have written that C of Q is contained in what is generally called the first obstruction set here. Obstruction meaning there is an obstacle for a p-adic point to be rational. And the obstacle, well, we have found one here. If we take all possible ones, we take any L prime here, vanishing on log of J of Q. And we look at L prime composed with log with iota -1 of 0. Okay. We have, well, this is the definition. And this is, again, obvious. So the work is to figure out when is this finite. And in such a situation, it is. All right. So that's the principle of classical Chabauty. I'll tell more about that tomorrow to enter the method in detail. But now I want to compare with the second method. Much more recent, quadratic Chabauty, which is due to many co-authors. I hope I'm not forgetting anyone who's been implied in the method, but basically, we find Balakrishnan, Besser, Dogra, Müller, Wittmann, Vonk, and others. I think it started in 2016, later. So the original version of this method was using something called unipotent groups and Selma varieties to generalize very much this. Oh, I should say Kim. This is all based on Kim's work before, well, Mignon Kim. The goal was to generalize this idea to much more general varieties than the Jacobian. I guess you'll hear about it in Nathan's talks in the next days. But for me, I've chosen to start with an alternative description which appeared in a preprint recently by Besser, Müller, and Srinivasan. Preprint of 2022, if I'm not mistaken. And I describe here the main ideas. So here, I start with something called a light bundle on J. I know what that is. And with some choices made before, some choices choices we made, make everything well defined. I start with the line bundle on NJ, and what the paper does is that we can build canonically something called a p-adic height HL, which goes from J of Q to QP. So first, if you know about heights, the usual heights, well, they measure things and they measure things with distances. And so they have values in R plus in general, okay? So they are used in many ways. For example, I guess you heard about it this week maybe. We often use the Néron-Tate heights on abelian varieties or Jacobians to measure complexity of points, of solutions, rational solutions. And this is very useful. Well, the idea here is to make the same thing, but with values in QP. So of course, you don't have any of the usual properties of heights, but still, as function, it will be interesting for us because I can say here, we can have the process of building heights, which is linear here. First, here, and now we'll define something here, which I'll explain afterwards. For the Néron-Severi group, it's called NS of J, which is defined as a Picard group of J, quotient not by the zero Picard group of J. I'll get back to it this week. But for now, just remember that this is a finite type dead module. So finitely many generators, and I call rho its rank. Right? So the quadratic Chabauty condition as opposed to the Chabauty condition, which I should have emphasized, which is here. Right. So the quadratic Chabauty condition is that the rank is less than, not G itself, but G plus rho minus 1. First, it's always slightly better because we can always find that rho is at least 1. So we have improved a bit the sum here. And the hope is sometimes, for example, when the rank is equal to G, if rho is at least 2, we can do something with this. All right. So I'll explain now what do we do with this kind of numbers. Maybe before I dive in, are there any questions? This? No, we cannot do R equals G because, well, in general, that's sort of conjectural, but we're pretty sure in general, if R equals G, the log of G of Q is really of rank G inside here. So there is no linear form isolating it. Sometimes, well, we cannot exclude it, but we think it's always what happens. If J is simple, I will describe some cases where the Jacobian is not simple and things happen, but otherwise, yes. Okay, so I'll keep on with this. So if you know about line models, you know we can pull them back here. So I can pull back, iota goes from C to J. So when I pull back, it goes from pcar of J, pcar of C. Okay, and also from pcar 0, it sends also to pcar 0 of C here. So defines a star from the Néron group of J to Néron group of C. And we don't talk often about the Néron group of a curve because, as I said, the pcar 0 of C actually can be seen as the Jacobian. And we can compute that, seeing all this as divisors, this is exactly measuring the degree of the divisor. Okay, so here, I take an element here, it's a divisor, and I can just take its degree, it's Z. So this is easy. All right, and now what happens is that if rho is larger than 1, what I can do, that the kernel of this has to be non-trivial. By dimensional arguments. So there is L on J such that iota star L is of degree 0, and L is not itself inside pcar 0. Okay, actually we can do better. We can modify L such that not only it's of degree 0 on C, but iota star L is the trivial line bundle on C. For every class here, we can modify in the same class to get something like this. And this allows us to define the following. So every element here, we can find a unique L prime like this and attach the height over there. So it goes from something like V prime to functions from G of Q to QP, like this. Okay. And so we get a map. Let's call it phi, which goes from J of Q to first the tangent space of JQP at 0 plus B prime dual. I'll explain right now how I do. Well, for this side, it's easy. It's just the log. So the p-adic logarithm, which I which I named here. Okay, so I can apply it to rational points. It sends me to QP of G, QP and it's more this. The quadratic side is here. I'll explain. Yes. Here, actually, maybe I can. Should I see? Oh yeah, I'll say it right now. This, how do I do this? Well, to P, I associate L, HL, FP. Evaluation at P, okay? So this will be, because L to HL is linear, this is really a linear form on V prime. So I get something like this. And now that's what the structure of the heights we built is very important and made for, is that if I identify now, if we look at this, these are QP spaces, okay? And this is actually additive. So we can define phi G, Q, QP to tangent space here plus V prime star. Now, if we take basis of all this, we get QP power G here plus here. I said it's rho minus 1 because actually that's the dimension of the kernel. I get rho minus 1 here after the choice of basis. And here, assuming I don't lose the rank, it's QP power R. And now what's miraculous with the method is that now I have a map from there to there, and it's polynomial. More precisely, if I go from there to there, it's linear because of the logis basically. But if I go from there to there, I get polynomials of degree at most 2. Degrees at most 2, which is one of the I guess one of the reasons why we call it quadratic. Another reason we can mention, I will not write it here today, but this can define changing the variety. We can use this also, this construction, to define bilinear forms on J of Q. So using bilinear forms, we get, it's pretty obvious where we think about quadratic afterwards. Okay, so that's what the miracle, one of the first miracles of the method. We get something that's polynomial here, okay? Between vector spaces of QP. And now, what happens with the hypothesis? Well, if R is less than G plus rho minus 1, this is larger than this, and we have a polynomial map, so it cannot be Zariski dense in the n space. There must be non-zero. What did I call it? Q, yes. Q inside QP with G plus rho minus 1 variables, such that, I should call it phi tilde, to make the difference clear. Here, Q composed with phi tilde E equal to 0 for all E in J of Q in particular. But it's also true for J of Q and for Q. So I managed to, it's really, if you think about it, it really looks like how I found a linear form here. I found a linear form that vanishes on the image of what was a log. Now I found something that's a polynomial, so more general, but vanishes on the image of rational points. Now the second argument is, as before, well, it has to vanish on rational points, but it has to not vanish on general points. Otherwise, I haven't said anything. If something is already 0 for the full p-adic points, I cannot really find anything. So that's the second point. And this is quite subtle as well. And from what I understand, it's maybe more, it's easier to understand with Kim's arguments and theory here than with what I'll do in a week. But what happens basically is that the image on C of QP is transcendental. So more precisely here, what happens? Here, I can write finite collections. Again, I have to split between residue spaces and also possible different values, which I will not get into. And a collection of locally analytic. So locally analytic means locally power series functions on this on C of QP, such that C of Q is inside the union T in T of the sets of rational p-adic points with Q composed with phi. I should say here it's sort of T of P is equal to sorry, I don't want to say anything wrong, but here ft of x is equal to T. And well, the link now, I cannot really give much more details, but this is something that's true for all rational points. And given how I constructed the heights, the HL, it turns out it's basically a sum of two terms. There is something p-adic and something that's, you can think of it as a constant. So if you look at this, you have to expand between the constant term and the p-adic term. And looking at all the possibilities, what happens is that if you think about the possibilities for the constant terms, the rest is a p-adic term. So it makes sense to talk about it for any p-adic point. And if I look at what happens for rational points, I get this, okay? So ft is sort of this when I really look at what were my heights and I expand the terms. And now these are locally analytic. I have this, but now there is something, again, a bit harder to prove is that, well, locally analytic functions on p-adic spaces are bad. If you have looked at it before, we can, for example, have one that's zero around zero and not zero elsewhere. So things could happen. But these ones are not, because, and I'll give some more names about it. There are some specific kinds of analytic functions, Vologodsky functions, and they do not behave that badly, okay? So they're non-zero. In particular, if they are non-zero in general or non-constant, they are not constant on any residue disk. So they do really make equations that are non-trivial. Because of this, every one of these space, each one of these space is finite here. So I do get finiteness of C of Q. As every ft will be non-constant on every residue disk. Okay, this is not trivial. This really comes from the way they were built. But yes. Good question. Well, in the case of equality, I guess, if if R is equal to G plus rho minus 1, I guess you have to assume some things, for example, that the Jacobian is simple. If you split into two parts, things happen that can prevent this. But otherwise, yes. I think, we'll see when it comes, but I think Nathan is the best place to answer this. I think there are some conjectures about this. Yeah. All right, and this will play the role of the second abstraction so this should be, I guess, C of QP 2. For example, you'll see other possible definitions on the docs, I guess. Okay, so that's what is the main idea of quadratic Chabauty. I should make clear now before I give details about all the methods. I consider myself, well, fairly knowledgeable about the classical method, the variance, also how it applies to modular curves but I will not talk about modular curves in my talks, sorry. You'll see applications of what I talk about in other talks, but I talk about general curves. So this I consider pretty well. Quadratic Chabauty is much more involved. As you can see, I did not dare name myself there. I'm not an expert on this. So you'll more see of how I understand this and how what can we get from what happens with the methods. Okay. So now I see I have some time, so I can start with the classical method. So the goal for this part is to explain in more detail everything I claimed here without any sort of proof, and see how it can actually make things effective. So effective, I should mention as well. When people say effective, they do not always mean the same thing. For me, there are two things we can say. First, you want to bound effectively the number of rational points. You want to say there are at most 10 rational points, okay? For me, this is an effective bound on the point, but it's not effective. What I really mean by effective is knowing the solutions, they are here, and I know there are no other ones, okay? So if you have an equation, I mean, knowing the solutions of the equations. I guess that's the most effective you can get. All right, as you'll see, in many cases, we can make of Chabauty an effective method. All right. So I'll start with some reminders of periodic power series. I don't know how much you know about this, but I wanted to give some basic results to convince you that it's really interesting to study them. That we're happy when we have zeros of periodic power series. So that's what we'll do. Okay. It's a little one, classical Chabauty. All right. So, as I said, I first give some reminders on periodic power series. So let's start by defining V, evaluation on the periodic closure of QP bar. So extending the evaluation of QP that's known, normalize with V of P is equal to 1. Okay, and V of 0, for convention, it's plus infinity. All right. So, I will describe what we can say about periodic power series, and the basic idea is we can say a lot. It's better than a for real power series. So let's F be a periodic power series like this with coefficients in QP and assume it's non-zero. Right? We will define something, call it Newton polygon. So I'll give the word for the definition and then I'll make a drawing because it's much simpler to understand. Newton polygon of F. What is it? It's the lower convex envelope of the set of points. I look at the set of points, and to each n positive like this, an integer, I look at the valuation of an. This is a relative integer, and I look at the lower convex envelope. So let's maybe do an example. Let's say f of t is equal to, I don't know, p plus p squared t plus pt cubed plus t4 plus t5, t5, etc. Okay. Well, what does it look like? First, I'll draw the points here. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. I start with the points P, so it's valuation 1. So it's here at coefficient 0. For coefficient here, it's P squared, valuation 2 here. For 3, it's 1 again. For 4, it's, sorry, for 3, so 0, 0, 2. Oh yeah, I forgot. Okay, this was p cube. Oh, well, good example. It was not on purpose, but let's say I forgot about t squared, so this would be at infinity there. Okay, now it's t cube. T cube will be pt cube here, t4 here, t5, let's say I put it here. Okay. Now assume that all the coefficients are over there are high up so that I'm not annoyed with the, the coefficients. I start here. I look at lower convex envelopes. I have to draw a segment that's below every point here. So it's this, then I do this, and then, well, depend. It might be this if all the points are really high, but otherwise it might be something like this, etc. So what happens is that I get a sequence of segments of slopes that has to be, at first it can be very negative, but then it has to go up slightly, up, up, up. And I can end up with infinitely many segments of finite like this. Or I can end up with an infinite segment at the end. For example, maybe I can do a second one. Look at this example. Well, let's say if it's p t plus p squared t plus etc. Well, pretty clear in this case. The Newton polygon is this. Okay, it's flat, infinite. So many things can happen, but the idea, and that's why I find it interesting. So this is a segment. It has a slope. The slope is basically here. So it's the coefficient. If I look at this as a piece of a fine line, the slope is this. Well, the slope tells me where are the roots of the power series. I'm not very precise. I am in the notes, but here I want to say, so proposition for a segment of the Newton polygon with slope alpha and length, the horizontal length. And there are n roots of f with valuation in QP bar in valuation minus alpha. Okay, I did not say anything about convergence of power series, etc. I referred you to the notes to check when it actually makes sense. But for example, if this was nice and the other coefficients are here, I can see here a slope. The slope is a minus 1/3 here. I have 3. The horizontal length is 3. So it would tell me that there are exactly 3 roots of f in QP bar, which have valuation 1/3. So it's very precise. Very precise. It allows me to figure out where are my roots in terms of valuation. So it's even more precise than for a complex case. Okay, and now I'll write some very special cases, which are the ones we focus on, at least for classical Chabauty, so that you see what it can say. And I'll do the drawings to explain what happens here. So let's take f on a slightly different form. Like this. an over n plus 1 t n plus 1. It looks like a primitive because it is. We'll see later how it comes about. And I assume that each an is integral, periodically. Okay, so it means in particular that all this is non-negative all the time. Now, I consider the minimum of the set of n here such that v of an is 0. Okay, assumed finite. Okay, so I assume one of these is not a multiple of P. All right, then I can know pretty precisely how many zeros I have in the residue disk. First off, I should say right now, with this, this converges on the open residue disk all the time. So as soon as T is a multiple of P, this converges and makes a solution. So that's the right situation to study. Here, as a function on PZP, which is also dQp 0, 1 over P, or even dQp bar necessary. Okay, you can study things on QP bar. So first off, here assume that n is less than P minus 2. Okay, have at most n roots of nth in, let's call it T. Outside 0, sorry. Because here, given how it's normalized, there is no first coefficient, so there is clearly 0 as a root. So I want to look for the other ones. The equality case is quite interesting as well. Here, at most, n plus 1 roots of f outside 0, and n plus 1 can happen and unless the worst case is n is equal to P minus, unless the valuation of a P minus 1 is equal to 0. All right. And the much more interesting case, at least for me, is that if n is equal to 0, I guess is the best case scenario. What happens if the first coefficient is 0? Well, it means that the 0 is here for your Newton polygon, but the second one is here. So you stick your Newton polygon by starting here. And this is very convenient. 0 is the only root of f in D unless P is equal to 2. Okay, the prime 2 is always a bit of a bother because I'll do the drawing. P is equal to 2 here. And then there can be another root alpha, let's say, with the valuation of alpha is equal to 1/2. Okay, I'll do drawings to explain. So here, imagine I have this. Well, as you can see, basically, we want to say that all the coefficients here should be p-adic integers, but it's not exactly true because n plus 1 can bring a denominator. But the first time it brings a denominator is when n plus 1 is a multiple of p. So n is equal to p minus 1 is the first case where we might have a denominator. Otherwise, we're sure we have everything above the line. All right, so here I have, if I assume this, let's say p is around here, p minus 1. What I say when I say that n is less than p minus 2 is that at first I have coefficients that might be with large valuation. And then I have n, which is here. Okay, and I know n is here because I'm not allowed to go here. So p minus 2, it still must be here. And p minus 1, I don't really know. It might be negative still here. Okay, and the first question is here, right? What happens now? Actually, I can prove that I have coefficients. I have Newton polygon that does something like this. Many things can happen, but what happens at the end is that afterwards, the slope has to be, it cannot be here, I should say. I did not draw it properly. Let's say they have something like this. Totally clear. Let's cheat a bit. here, because as I said, the slope has to go up at every segment. Okay, so this is possible. Basically, what I'm saying is that there is a slope that's negative, so it's a minus alpha. But the minus alpha the alpha is too small. So I'm out, when I look at valuation equal to alpha, I'm out of this disk. So and it will be even worse for the other slopes because they will go up. It means the norm will go up here. So the other solutions do not work. The only possible solutions inside the disk are the ones who have small value slope like this. And this is how I get something of length. Oh, sorry, it's n+1 here. Because I look at an over n+1 with in quotient t n+1. So I get something of length n+1, as I said. But n+1 means I have n+1 roots, but as I said, 0 is an obvious root. So I do get at most n roots of p. Okay, this one was a bit difficult to draw. You'll see that the case C is much easier. I'll do this maybe here. Yeah. Case C much easier because we start with 0. Case C here happens at 0. I go to infinity, doesn't count. At 1, I am here. Okay, the Newton polygon starts here, and let's say that P is here. This one, P minus 2. Okay. Well, what happens is that basically all the other ones before P minus 2 are, let's say, around here, and then the first one that can be negative is at little n is P minus 1, so here, but it's not too negative because the valuation of P is a -1, so at worst it's there. Okay, and the ones afterwards will not be much more here. So I get here, I get the first slope that's already too bad to land inside D. It's too flat. It's too flat. I'm not in the disk of radius 1 over P. So there is no solution given anywhere except there is a 0 solution. All right, this is if P is larger than 2. If P is equal to 2, something quite special happens, which I'll do right now. Of course, I explained it in detail in notes. If you want to do it as an exercise, it's an exercise of calculating valuations and figuring out this valuation of this cannot be too small when these are integers, etc. So if you want to convince yourself, what happens now if P is equal to 2? Well, let's say so 0, 1, 2, 3, etc. So at 0, I'm up here. At 1, by hypothesis, if I assume n is equal to 0, this one is up here, okay? But now, what can happen at 2? If v of a1 is equal to 0, I can get here. And this will give me slope exactly -1. Oh yeah, sorry, yeah. I am French, so I should write this. Yeah. Okay, for me, n always includes 0. Sorry about that. Okay, here and the rest is not a problem. Here you can compute that the rest doesn't have a good slope, but this means exactly one root with valuation 1. So norm P, oh no, 1 over P, sorry. So it's exactly inside this disk. That's the only bad case that can happen. 1 is equal to 0, that's this case, and there is one other root. Okay, so I have 25 minutes left. All right, I can now tell a bit more about the setup of the method in terms of algebraic geometry. Are there any questions here? I just wanted to convince you with some examples that if I know the function here, I can figure out where the roots are, the Newton polygon. All right? Okay. So basically, if you don't, maybe at some point in the next 20, 25 minutes, you will not understand what I'm doing. Keep in mind, I want to end up with local equations with power series, okay? And if you ask yourself, what does it mean, a local equation on a curve, right? You have to make it explicit somehow with a curve that's given by functions. It's not clear how to make it. I'll explain now how to formalize the fact that we look at local equations. And it includes finding good parameters. I want to parameterize my curves, so that's how I will explain things now. And also, I think Mr. Gattet mentioned it. A lot of what I will be doing in many, I guess, many of our talks, a lot of difficulties are coming from the fact that we have vector spaces, we have rational structures, but we need integral structures to reduce mod p, to do things like this. That's one of the real difficulties of the theory. You have to be clear at all times, what does it mean to be integral, okay? And that's also what I'll try to do here in this first situation. Okay, it'll be this. Well, let's see what allows us to talk about parameters, etc. Okay. First, I should mention I defined what's a residue disk for. It was, yeah, I have fixed a model, so a smooth projective scheme over ZP. Actually, it works for anything that's smooth and proper. Even just proper works, but I will just say smooth all the time. So it works in any dimension, and I'll do it now because I need it for something later. But if you want to stay on the case of curves, I'll end up with this, with a nice description of everything that happens. So let's sky here. The P be a smooth projective of relative dimension D. Okay, if you don't understand what this, well, you have a bunch of equations defining something of dimension D with coefficients in ZP. And the fact it's smooth means when you reduce mod P, it's still something that's of dimension D everywhere, and there is no problem with the defining the equation. They define something that's indeed smooth. Okay. Then for any x in x of fp here, now you can think of this having two parts. There is what lives above qp and what lives above zp, so fp. So generating fiber, special fiber, and this is a point inside the special fiber. Okay, so you can also think of this as a point of the scheme when you just look at what lives over fp. I'll describe a way to find good parameters to analyze what happens around this point. So the maximal ideal of OXFP X here, because it's this is because of smoothness, something smooth of dimension D here. So the maximal ideal can be generated by let's say T1 TD bar generators of the tangent space, let's say tangent space, so mx x over x squared. So this is actually the cotangent space. So I can find generators, degenerators of some space, and I can lift them so that they end up generating this. Okay, the maximal ideal here. And now, once I've done that, I think what I will say now, basically, if I start with this, it extends to everything I want. What does it mean, everything I want? It means then maximal ideal of O x x. So now I'm not looking at the fiber itself, I'm looking at the whole space here. So it's not something over FP. Here, it's generated by T1 T. Oh yeah, I should say T1 TD. Yeah. Okay, so I consider, so to sum up, this is a vector space of dimension D. I fix generators, then I lift them back to MXFPX. I get T1 TD, and I prove that they generate the maximal ideal. Then they also generate OXX together with P, because here basically this tensor FP gives you back this. Okay, so that's where it comes from. And then if P, a QP point, has reduction X not P, okay, we can evaluate T1 TD at P. Yeah, and T1 of P, TD of P is equal to 0. Okay, here, because we can think of them as rational functions on I here. Actually, here, T1 TD generates O X QP P. So the ring now around P, but inside the generic fiber here. And because of this, it generates, it's fine, and it gives a description. We call so T1 TD a good system of good local parameters at P. And we can also say T1 TD modular parameters at X. Okay, because they generate the maximal ideal where I want. And if you don't understand why I talk about parameters, wait for the next result that explains a bit more precisely what we can do with them. But they are, let's say, nice generators of these spaces. And with these definitions, and assuming there are good systems of parameters here, well, I have here, so I can define first something like this. To a polynomial in T1 TD, I associate, well, to Ti, I associate Ti. All right, this is well defined. Yes. Here, yeah, it's P T1 TD. Yeah, it's really at X, but X seen inside Chi and not Chi FP. That's the difference. I have to. I don't know. Maybe I should. Let's say, yeah. This is Chi QP. This is Chi FP. All right. So in some sense, X lives in this. But if I look only inside Chi FP, I'm there. But given how the topology works, really, it's more something like this when I look at the full ring of parameters. So this will give you OXX, and this will give you OXXFP. Right? And I said in particular, this is this tensor P, FP. So when you reduce mod P, you get back to this. And we need, here it's important, again, for integral structure, it's important to think about it this way. So I can associate, naturally, if I any variable Ti, I associate the parameter Ti, Ti here. It's well defined. It sends a maximum, it's in ZP to, well, what is ZP here? But actually, it's not an isomorphism in general. It's much more complicated than that. But we don't care because we want to figure out an isomorphism. And the way to do this is to extend to power series. But of course, it doesn't converge necessarily here. So the right space where it converges is a completed local ring. Okay? And once I do this with a completely local ring, this ends up being an isomorphism. Okay, so the local ring itself is not very easy to describe in general, but the completely local ring is really a ring of power series, which is why it's more convenient. All right, and let's say I. And even better, if you think about the equivalent definitions for XFP and X for P here, it works with QP instead of ZP or FP instead of ZP, and everything is what you imagine in terms of commutative diagrams. So with this, just with this, I have a description of the three rings, this completed, and the one for P. So it allows me to describe this, and now I can explain what the parameterization can be. For those who know about schemes, I have dx, so the residue disk here. Let's recall what this is here. Of P inside of X of QP, such that P bar is equal to X. Okay. So because chi is proper, I can define for any such point, I can define a ZP point. In other words, I extend any QP points to a morphism from spec of ZP to chi, and asking this to be X means when I look at the morphism from spec ZP to chi, the image of the point over FP is little x. So basically, it's this. And then I use the scheme theory to say this is the same thing as looking at morphism of local rings OX, X hat to ZP. Okay, so this is a canonical identification. And now, well, this isomorphism of local rings, I want to look at what this means, but well, now I have a description of this morphism. So it's the same thing as looking at morphisms of local rings from ZP, T1, TD to ZP. And this is choosing a value of T1, TD also so that everything converges. So the only thing you can do is prescribe values of T1, TD, which are in P, ZP. So this is, so to say F here, F composed with phi of T1, TD. Okay, so which is why I bothered with this description, which is very abstract, at least for me. Once I have this, I can parameterize the residue disk by PZP power D. And I retrieve what I said before with the curves. For curves, for D is equal to 1. So I really look at PZP. This? Yeah, for those who know better about schemes. So I start off with P from spec QP to chi, okay? So because this is projective, so proper, it's called the evaluative criterion properness. So that's just last time. Yeah, this extends, okay? So P tilde. Now, because of this, I have an image of something which is spec of FP. And asking that the reduction of P mod P is little x is asking that this morphism has the image x. Okay, and now you can factor through, or you can factor here, like O, x, x. So here actually. And now morphism like this is a morphism from OXX to ZP. And you can complete it, you're allowed to when you look at morphism of locus. So it's this, and now once you have this, you can identify directly with this. All right. It's chasing the identification, but it's not very difficult. So at the end, we start with a point here. and we get this. And if you think about it, it's basically same thing as looking at T1 of P, P, D of P. It's also, there can be a definition. So it's called evaluation at P. So I do have a nice way to describe what happens around X. And it really is, here we often talk about a polydisk because it's, well, multidimensional. Here it works. Okay, I have a few minutes to conclude, well, for the case of curves. And for the case of curves, I think you'll recover many things you already know. It's definitely a bit simpler. For curves, we want something that vanishes at the points, that's not too much, and to retrieve everything else with it. And we want to do it not only sort of over the field QP, but also integrally, so it has to work as well for the reduction. So the basic idea is we want a function that vanishes at the points, but with order 1, and that so that its reduction vanishes at the reduction at the point, also with order 1. Okay, and well, basically I've said it all. When we think about it, if I pick P over ZP such that, let's say C Q is equal to my curve C, okay? I could also say C over ZP, the complete ring, so that CQP is equal to CQP here. So we can fix T inside O CX, a good local parameter. That's T is a good of local parameters. And then what can we say? Well, the X is morphic to EZP by what's said here. Also the disk, again, I'll say it, but disk in QP of radius 0, 1 over P here by evaluation of T. And now it might be, if I take a point P above X, if P in C of QP is such that bar is equal to X, in other words, it belongs to the residue disk, well, it can be that T of P is non-zero, but it's not a problem. I just take SP to be T minus T of P here. Okay, and I can think of it as a function inside QP of C, so the function field. It's really a function of a function field. It vanishes at P by construction. And then SP bar is, so SP is a uniformizer. That's the usual word for curves, uniformizer at P. And SP bar, which I can think of is FP of TFP, which is also TP bar, is a uniformizer at X. All right, and now I can write a complete description of the local rings because of this. So OC X, ZP here. Let's say extend it to ZP. Here's the same thing as ZP applied to SP here. I can look at the point P here, and it will give me QP of SP. And I can look at the point the FP X and ZP bar, SP bar, and all this commute, so it's T bar. And when I tensor by FP, I get this. When I tensor by QP, I get this, and same thing here. All right, so basically I can think of this as the integral structure on the rings, and I can reduce mod P or go to the field tensor QP, which will allow me afterwards to do quite subtle computations with this. And this will be called good uniformizer. Okay, in particular, what I'll do next, you have a few minutes bonus. What we use it next is to, well, we want to do things with this. So we'll have to show, well, now you know every function that's defined around P, because of this, every function that's defined around P belongs to OCP. And so you can expand it in power series in the uniformizer for a curve. So now you know what this means to have a local equation. If you know a function, or you want a function equal to 0, you will be able to make sense of it as a power series, okay? But actually what we'll do first is we will define this using differential forms. So we also need to be able to expand in power series differential forms. I'll do a bit of that tomorrow. And afterwards, I will integrate differential forms because, well, this is the integral of an Tn, okay, dt. When you integrate this, you get this. And that's what we'll need to do to be able to, afterwards to calculate and find equations for your rational points. Okay, I think I'll stop here. And again, we'll see, I'll send the lecture notes as soon as possible so that you have more details about this with the proofs, etc.